Welcome to SPT online classes, and today we are going to discuss the concept of touching. In one of my previous videos I mentioned that two matter can never touch. From there onwards I got a lot of enquiries from the students just to explain this concept of touching once again exclusively as a separate video. So here I am going to mention about the concept of touching. So let's discuss this spooky action. Yes, it's true that when you take a scissors and you cut a piece of paper, the scissors is not touching the paper. When you take a knife and you cut a cake, the knife is not touching the cake. When you sit on a chair or on a table, your butt is not even close to the table. When you write using a marker on a whiteboard, the ink from the marker is not touching the whiteboard. Yes, emotionally it's hard to believe that when you touch your loved ones, when you touch your family members, it is not touching. The concept is interaction. So let's see what an interaction is. For understanding the concept of interaction, let's see it from an atomic scale, because we want to know what's happening in an atomic level, whether we are interacting with any matter. If there is no touching happening there too, then we have to go to subatomic level. So let's see it from the atomic level. Here you can see two atoms coming close to each other, and what's happening to the potential energy between these two atoms. The potential energy is increasing, the repulsive force is increasing. There is no way that the nucleus of these two atoms can touch each other because the repulsive force is too high. So you can see the van der Waals force of attraction initially. Okay, if I just leave this, the van der Waals force of attraction make these two atoms to come close up to a little bit, but after that it's all the repulsive force of action. The electron overlap action make these two atoms to get separated, and they will lie in a stable gap. Understood? So the potential energy always try to be in a minimum position, so that whatever you try to do on two atoms, when they come close enough, the potential energy is going to increase beyond a point. Got it? So in an atomic scale, two atoms are not going to touch. Hope you understood, because we are focusing on touching here. So at any cost, two atoms are not going to touch, but they interact. They interact by sharing electrons. We call it bonding, whatever, but the concept of touching is not happening over there, because if you take two nuclei, they both are positive. Once they bring together close enough, the repulsive force action will dominate and they will never touch. Okay, so we understood that two atoms are not going to touch each other, they interact. But what about in the case of friction? In the case of friction, we might have a misunderstanding that when you keep two objects close enough, they touch each other. Let's see whether they touch or interact in this concept of friction also. Okay, here in this simulation you can see two books close enough. One is book of chemistry, the other one is a book of physics, and you can see the friction between them. Okay, there is no way to edit this, otherwise I would have taken one book as evolution and the other one as creation, whatever. Here the blue book consists of a layer of electrons. You can see these blue spherical balls are the outer layer of electrons of the book of chemistry, and the green electrons are that of the physics. Okay, once they come so close enough, what will happen is that this electrostatic repulsive force takes some electrons out from the way. What you can see is the temperature rising up, and the maximum distance that you can go near to a physics book is this much. Beyond this, what's happening is that the first layer of electrons, which is blue in color, cannot go into the green layer of electrons. So this is the maximum distance that you can move. That means here you can see exactly that it's still not touching. Even in the electron level, two matter is not going to touch because of the electrostatic repulsive force. This is what exactly happens that in the case while you take a scissors and cut the paper. The electrons on the edges of scissors, while it comes closer to the paper, the electrons on the paper is moving away, making way for the scissors. Understood? If you take a knife and cut a piece of cake, what's happening is that the electrons on the edges of the knife, while it comes towards the cake itself is splitting away. It's making way for the knife to pass on. So that is how the electrostatic repulsive force work. Okay, so we understood that even in the electron level, the concept of touching is not happening. What about in the case of a proton-proton interaction, a positive-positive charge interaction? Where can we see that? There is an example for that, Rutherford's alpha scattering experiment, where we can see the proton-proton interaction or the positive charge interaction. Let's get into that. Yes, Rutherford alpha scattering experiment. In this case, the gold nucleus is being hit by a stream of alpha particles. That's how we used to study, but can I use the word hit? No. A gold nucleus is being interacted with alpha particle stream. Let's see that first. What you can see here is the gold atom is being consistently being tried to hit by alpha particles, but not in a single case the alpha particle is coming so close enough to a gold nucleus. The reason is because of the electrostatic repulsive force. We know that protons and protons will always repel, so there is not much to think in this case, I guess, because they are not going to ever touch each other. Even you can see that I'm changing the energy. If I'm putting the energy to minimum, you don't even have to bother about alpha particles will hit the gold nucleus or not. But once I increase the energy and put it into the maximum flow, even in that case, alpha particles are not going to hit the gold nucleus. The reason is because of the electrostatic force of repulsion. Proton and proton always and always repel. So in this case, we concluded that even in the case of two protons, they are not going to touch each other. But is there something left out? Is there any case that we have left out for the interaction case or the concept of touching? Yes, there is something. Let's get into that. Okay, now we started from atomic level of interaction, we went through friction, then we passed through Rutherford's alpha scattering experiment. Now here we are, some more closer, nucleon interaction. What about the case of protons and neutrons? Are they touching each other? So what you have to understand is that nucleons, how strong they are when it comes to close proximity. You can see this graph where as the nucleon's distance move closer and closer, the potential energy is increasing, which we have seen in the case of atomic interaction. So within the range of, you can see that what is the range? You can see beyond 2.5 Fermi, the potential energy is almost zero. Once the distance is coming closer and closer, okay, the potential energy is increasing. Means nucleons, they interact but they don't touch. They interact using particles called as gluons, subatomic particles called as gluons. They interact using the fundamental strong nuclear forces, but they are not going to touch again. A proton which is made up of quarks and neutron which is also made up of quarks. Two up quarks and one down quark make a proton. Two down quarks and one up quark make a neutron. They interact with strong nuclear force. Means once a proton comes so close enough to a neutron, they are bound by the strong nuclear force of attraction. Got it? So one proton can't go beyond a limit. One proton or a neutron cannot cross the line, the boundary line. Understood? So they interact, they are not going to touch again. Now what's left out? Let's see. Something that we cannot neglect is the case of the electron capture. What's an electron capture? Once again, I have mentioned in a previous video, where in an electron capture, what's happening is that when protons are so much inside a nucleus, it becomes unstable because there should be a ratio between the count of protons to neutrons, and once it goes down or once it goes out of the way, this proton or this nucleus will become unstable. What will happen if a nucleus become unstable is that it grabs an electron from the K shell. We call it the K electron capture also. Once an electron is being grabbed from the K shell, it moves towards the nucleus. What will happen? A proton combines with an electron to form a neutron and a neutrino. Here you can see, electron is being grabbed into a nucleus where a proton, which is made up of 2 up quarks and 1 down quark, will convert into a neutron as well as an electron neutrino, where you can see that 1 up quark is getting decayed to 1 down quark. This is the point. This is the point of interaction where you can say at least that a positive charge and a negative charge come so close enough. They came so close enough for a concept of touch. Again, all we speak in terms of forces. Here also we speak in terms of interactive forces. So it's not about the concept of touching that we used to say in our real life, in our normal life. It's all about interactive forces. Understand? So here what's happening is that a proton interacts with an electron, and this interaction is the closest interaction. Understood? And that proton gets converted to a neutron and a neutrino, where that neutrino will be shooting out from this particular nucleus along with the X-ray radiation, because since the electron is grabbed towards the nucleus, there will be a vacancy into which another electron will be jumping from higher orbital to that, releasing the energy in the X-ray spectrum. So this is the closest approach you can say, but again it's not touching. So whether there will be a concept of touching anywhere in the case of universe, is there any case of touching happening in the entire universe? In the last case, in the concept of touching, neutron stars, dead stars basically, after the supernova explosion, the stars will remain depending upon the size and density. Some stars will turn into neutron stars. In neutron star, you can see the atoms will get squeezed enough. Nuclei will get squeezed enough into the core of the neutron star. At least you can say that the protons are smashed towards, or they are squeezed enough so that at that point we can say that is the shortest distance between two protons or two neutrons. We are not sure about what's happening inside the core of a neutron star, but still we can say that because of the immense pressure, because of the immense density of a neutron star, the core of the neutron star is the point where you can say the closest point of touching. Because of the ignorance about the core of neutron star, we don't have much information about it. But we know something, that it is the point of highest density. More than that, you can find this much density in black holes only, which is once again a dead star, which is once again comes after the supernova explosion, and that happens if the star is so big enough. Okay, so here this is also a byproduct of supernova explosion, where comes the neutron star, and inside the neutron star is the point where you can find the possibility of the closest of touching. So from this video, I hope you understood that if you go and smash a bottle, now you can tell to your parents that you haven't done that because you can't ever touch a bottle. Understood? Now you can pluck a mango, or you can beat your friend just for fun, not to be serious. And again, you can claim that you haven't touched your friend. That's all for today. Thank you for listening. Have a great day.